How complicated can that be? I'm going to try to distill this down to the basic information that you need, and hopefully you'll recognize that it's not very complicated, but it's very critical. So let's start out with the functions of saliva. First function is lubrication. So lubrication is going to come in two forms. One is water. The other is mucus. So we'll look at the structure of the salivary gland in a second, but water and mucus will be secreted in large amounts into the oral cavity, and this is going to be providing lubrication for the food to make sure there's no choking response. The next one is salvation. Not salvation, but salvation. What is salvation? Okay, let's go back to general chemistry. What is salvation? Dissolving substances in water. And why is this so important to us? What do we have on our tongues that's very important to our emotional health? Taste buds, yeah. So after Dr. Hartley and McGuire's quizzes yesterday, I bet all of you probably ran over to Dairy Queen and grabbed a Blizzard because it was just so nurturing to the soul. Actually, I saw your results. The class average was 87, so nice. Excellent. Oh, you didn't see this? I thought they released it already. Okay. Yeah, the average was 87. Nice job. Okay, so this is involving taking water, taking small molecules from our food, putting it into solution that bind to our tongue. If we didn't have this material, these ligands could not bind to the receptors and trigger any kind of taste sensation. Oral and dental health. Rinses teeth, buccal mucosa, and this is the big function. Lysozyme. So lysozyme, many of you that took undergraduate labs may have used lysozyme. We use it in the lab all the time. The purpose of lysozyme is to digest a bacterial cell wall, because the cell wall of these gram-positive bacteria have these peptidoglycans, these carbohydrate sugars that are all cross-linked to form the wall. And this is what maintains osmotic control in these bacteria. Lysozyme is the enzyme that hydrolyzes these sugars, pokes holes, and without osmotic control, the bacteria lyse and die. So the antibacterial function of lysozyme. Lactoferrin. Lactoferrin is a chelator. Again, general chemistry. A chelator is something that's going to bind something else. Typically, we talk about chelators binding ions. In this case, lactoferrin will bind iron. Taking iron away from bacteria does what to the bacteria? What's the biochemistry? Here I go already, right? What's the biochemistry that requires iron? You all know this. I know you do. It's a prereq to get here. Iron, electron transport chain. Remember that? Energy production. So without iron, the bacteria are going to be deprived of energy. IgA. So Dr. McGuire, when he talked about histology, he talked about the lining of the gut. Fortunately, the histology of the gut from one end to the other is really very simple, with a couple of exceptions. And he talked about the immune system. So if you collectively take the entire immune system that is adjacent to the luminal cavity of our entire gut, put it all together, it's the largest portion of our immune system in the body. Our immune system does not start in the gut. It actually starts in the oral cavity, because the salivary secretions will include IgA for immunosurveillance. Okay? Now, Let's look at salivary structure. So this is something that you'll have to get used to me. I draw things out because I like to take things stepwise, one point to another. So I'll be doing this kind of dot cam activity. I used to do everything on the board, but it doesn't pick up on lecture capture very well, so the media services told me, shift over, get 21st century. So here I am. So, structure of a gland. So this is the basic unit of most glandular structures. What we have here is the acini structure. So this is composed of the secretory epithelial cells. So the epithelial cells are going to be lining this entire structure, and their job is to produce all of the salivary factors and be able to secrete this material in a directional manner. So secretion will be occurring through the apical surface. Now, once it gets into the lumen of the acinar structure, then this material has to move. And it is going to move down the duct, the salivary duct. Now, there's two portions to the salivary duct. The first portion is called the intercalated duct. The intercalated duct is essentially the neck of an acinar unit. And these are very, very simple, short, squatty, cuboidal epithelium. Their job is to do nothing but just form a duct, form a tube. Once we pass this intercalated duct, then we get into the rest of the ductal system throughout the rest of the salivary gland. And this is called the striated duct. Now the striated duct is also, it's kind of they look histologically like cuboidal cells, but they have a lot of function like epithelial cells. Now, what do I mean by that? What we're going to look at in a minute is we're going to look at the secretions of these epithelial cells in the acinar units, and we're going to look at the material, the fluid, the salivary fluid, that ends up in the ducts. And we're going to see that these are two different types of material. Yes?
When you say they function like epithelial cells, do you mean like squamous cells or?
No, they function more like columnar epithelial cells. And what these cells actually have are a huge lot of ion transporters. So epithelial cells are what we're typically used to as having lots of activity going on. Lots of material being absorbed, ligands binding to receptor, ion flux going across the membrane. These striated ducts, these cells, are going to be modifying the salivary fluid. They're going to modify it in a very, very specific way. Okay? So, what else do we have on these particular epithelial cells? Well, one of the things that we know that occurs is that if you see something absolutely delicious and tasty. Now, for me, I'm already starting to salivate because I'm thinking about what I'm about to say. Dunkin' Donuts, frosted donut, chocolate, fry cake with a nice cup of coffee. Okay, some of you are offended by that, but some of you, I bet, are salivating when you start thinking about something like that. So salivation typically means that we're taking more material and pushing it through the ducts so that we increase the amount of salivary fluid that's occurring. In order to do that, we have a cell layer around each acinar structure that is smooth muscle-like, and that's the myoepithelium. Myo for muscle. So it's these particular cells that are going to perform the contraction that is going to increase the rate of salivary fluid secretion into the oral cavity. Now, I use this word apical. And the reason I use this is because I like to take a little bit of a tangent, because this is an incredibly important property of the entire gut. And we're going to be revisiting this over and over again. So if we have our epithelial cells, these are 3 cells adjacent to each other. This up here is the lumen. And that is where the secretory products need to be placed. So that means we need to take material and transport it into a unidirectional path. Now, we have what's here called pericellular space. Now, you would think that it would be very easy, possibly, for material in the lumen to come back around through the pericellular space and get back into the tissue of the body. What we have specifically on these epithelia are the tight junctions. And Dr. McGuire showed these on some of those pictures of the epithelium. Now, the majority of epithelium in the gut has these tight junctions, and that's because what we want is a process called regulated transport. The job of these particular cells is to put material, components of whatever they're secreting, into the lumen. Now, this is going to be very, very important because we need to control what's going through this epithelial barrier. When Dr. Ma comes in with Dr. Strickland, they're going to be talking about inflammatory bowel disease. So inflammatory bowel disease is when we get a disruption of this particular tight junctions across these epithelium, and now we get food products, foreign material that can enter our bodies, causing an inflammatory response. So that's why these junctions are very, very critical in maintaining the integrity of the epithelium and also controlling what's moving back and forth. So now, you'll also read in our text readings about the 2 types of acinar units. There is a distribution of what is called serous and mucus producing epithelium. So some acinar units will produce more watery secretions, meaning serous, and some acinar units will produce more mucus secreting. Now, as you read about this material, you'll see that our 3 types of salivary glands, the parotid, the submandibular, and sublingual, will have different ratios of serous versus mucus. That is a piece of information that is not necessary, that level of detail for the block. Knowing that there is 2 types of secretion, serous or mucus secreting, that's critical, okay? So now, how is all of this regulated? So here is our lumen of our salivary gland, of our acinar structure. And we need to be able to control the saliva. So under normal, what we call resting conditions, we have a continuous secretion of material from these epithelial cells into the lumen of our acinar structure. So this secretion is occurring all the time. And this is important for our oral health because even when we're not eating, we need to make sure that we're getting these antibacterial substances into our mouth. Now, you'll notice a difference under resting versus eating. Under resting conditions, every now and then, maybe every few minutes, you have to swallow. And that's because you continually have secretions coming out your salivary ducts, filling up your oral cavity, but it's not much. But as soon as you start eating, or even better yet, you see food, now your salivation rate increases dramatically. So that means that there must be some sort of connection between your brain and your salivary glands. So let's look at the first of 3 phases of digestion that we're going to be going through. The first phase is called the cephalic phase. This phase here is the Pavlovian response. So all you have to do is see or smell food. And what happens? You start to salivate. So I will talk about higher centers detecting senses like that from the neck up, because this is neurobiology. And God bless people like Dr. Shuttleworth, because this is, to me, is a black box. It's very complicated. I've spent my life working from the neck down. So I will talk about higher CNS centers. Higher CNS centers that you are seeing or smelling food is going to trigger a response. And that response...
Can't see. We can't see. We can't see.
Oh, thank you.
Scoot the paper out first.
Much better. Okay, so the food thought, the food senses will trigger this CNS response, and this is going to trigger a response to the salivary gland. Now, do you think this is a very obvious question, do you think it's autonomic? Does that sound reasonable? Pretty much. Do you think it's sympathetic? Yes and no. Right? What happens when you get scared? Something happens over here. We'll talk about that in a second. That's even more complicated. How about parasympathetic? Yeah, parasympathetic pretty much is the gut response. So the parasympathetic is going to be binding and sending its neurotransmitters that are going to make contact with the salivary epithelial cell. So we have 2 different neurotransmitters that are going to be controlling the salivary secretions. The first is acetylcholine. So the acetylcholine response is going to be the absolute major response. These are going to be triggered through M3 receptors, muscarinic receptors. And then what response is this going to elicit? What's the signaling path? Don't ask. You just saw that from Dr. Shuttleworth. Yeah. Phospholipase C, IP3, calcium. That's the mantra. Keep that going. And then this is going to cause vesicular fusion with that apical membrane, and the contents of those vesicles will be secreted into the lumen. Now, what about this response here? A sympathetic response. Now, normally what you would tend to think is that the sympathetic response is going to be the counter. It's going to shut things off. In this case, whenever you have a fight or flight reaction, you're actually going to be increasing the activity of your salivary gland. So this is just the opposite of what we normally experience. So this will work through the PLC IP3 pathway to increase the amount of calcium, to cause increased secretion of these vesicular contents. Now, this path is considered a minor pathway. The difference between major and minor is that this will induce the greatest amount of secretion through the acetylcholine pathway. Now, what are the contents that are being secreted? Well, we have, first of all, ions. These contents are largely proteins. The proteins, of course, are being synthesized by the epithelial cells themselves. And these proteins include our lysozyme, our lactoferrin. We'll talk about another one called amylase in a second. And then the ions are being transported by transporters, the ion transporters, from the cell into the lumen. Now, where do these ions come from? Can't be synthesized by the cell. So they're coming from the blood. So what this means is that we need a coordination in our neural signaling between activating these pathways for secretion and also vasodilation. So the neural signaling here is not only going to be signaling to activate the salivary secretions from these ducts and these glands, but it's also going to induce vasodilation so that we increase the blood flow, increase the water, and increase the ions that are available to these epithelial cells for secreting into the lumen. So we've got ions and proteins going out. We also know that we have a lot of liquid. It's a big serous secretion. So how does this water get into the lumen from the blood? How does water respond to ion changes? Ion concentration changes. It goes to the higher concentration. Now, I'm bringing up these kind of basic points because we're going to see a repeated theme over the next couple of weeks with this principle. So the ions are flowing out through these transporters, and water is moving through the pericellular space because of the principle of osmosis. So the water will always follow the higher concentrations of ions. The water can also pass through the cell itself. Through water channels called aquaporins. Okay, questions so far? So now we've got our ions in the solution, in the lumen. We've got our proteins. We've got water flowing in there. We've got stimulation from the cephalic phase because of this thought of food, which which increases the activity of those myoepithelium to cause contraction, and it also causes vasodilation to increase the amount of blood flow, meaning water and ions, to get to these epithelial cells. Now, what are these ions? If we look at this as our acinar unit, and now we're going to do a microphysiology experiment. We are going to take a small syringe, and we are going to withdraw a sample of fluid from this luminal cavity of this acinar unit. And if we do that, and we look at the concentration of ions, we're going to see sodium, potassium, chloride, and bicarbonate. So of course, those are the major ions in the blood. They're coming from the blood. Here's the concentration of each of these ions in this luminal cavity, and this is called the primary saliva. Primary because it has just been secreted and located in this lumen. Now, if we do the same extraction of putting in a small syringe and taking a sample of fluid downstream, what we're going to see is the secondary saliva, because it's downstream from the primary, has a very drastically different ion concentration. Our sodium decreases substantially, potassium increases, chloride and bicarb decrease. So the fact that the primary saliva has this concentration of ions, which is similar to blood concentration of these ions, this is considered isotonic, which means that we have a good balance of ions and water. Now, as the salivary secretions start moving down these ducts, the concentration of ions change. So that indicates that there must be some sort of transporter activity going on by these ductal cells. What generally is happening is we're withdrawing the ions. So we're removing ions from the secondary fluid, and therefore we are going to be ion deficient, water heavy, so it becomes hypotonic. Okay. Now, when we talk about transporters, we're going to be talking a lot about transporters. We have many different types of transporters in the gut, again, because we need regulated secretion and regulated uptake, absorption. And so everything that is in the lumen of the gut, inside the tube, is equivalent to outside the body. So that means we have to control everything coming into the body. The best way to do that is not by simple diffusion. We need transporters so we can regulate this uptake. So what I want to do is just review briefly the different types of transporters. So a molecule that can go across the plasma membrane, that is simple diffusion. If it does not need any kind of protein transporter, it does not need any assistance, it can come across this plasma membrane without any assistance. What's the property of this molecule have to be in order to cross the plasma membrane without a protein assistance? Lipophilic. Now, lipophilic transport is something that we definitely don't want to do under normal conditions because this means free passage across cells. However, we take advantage of this with pharmaceuticals. pharmaceutical drugs. If you have a pharmaceutical drug that is very hydrophilic, it's not going to cross that gut barrier very well unless you've got some sort of drug transporter. And we'll go into that in a couple of weeks. So if you have a drug that is very lipophilic, that is able to transport across that epithelial cell by simple diffusion, and you can get the drug into the body. So this process is taken advantage of by pharmaceutical development. Now, the real big one that we're going to be talking about a lot is this one, the sodium-potassium transporter. This is called an antiporter. It's an antiporter simply because it is one protein embedded across the membrane, and you have sodium and potassium ions that are transported in the opposite direction. And this transporter will not work unless you have a sodium and potassium bound to the specific protein. So just binding one ion will not trigger this activity. What else is really important, critical about this protein? It's an enzyme, right? What does it hydrolyze? ATP. So this is an ATPase transporter. So what this transporter is able to do is create a chemical gradient. And the chemical gradient that we are going to be generating is the sodium gradient. By generating a sodium gradient, what we are essentially doing is taking hydrolysis of ATP, that energy, and we're transposing that energy into potential energy by creating a sodium gradient. Sodium high concentration on one side, low on the other. That's primary active transport. Now, if we generate this gradient so that we take the energy of ATP hydrolysis and put it in another form of energy as this chemical gradient of sodium, we can take advantage of the sodium gradient to drive another transporter. What this is going to do is we're going to use this sodium gradient by dissipating the energy that we've stored from the sodium gradient. We are going to drive in another solute. Sometimes this solute could be driven in against its own concentration gradient. So you can imagine when it's really important to take up molecules from the lumen of the gut into the body's not going to take advantage of a simple gradient. A simple gradient would be called facilitated diffusion. Facilitated diffusion is when you have a concentration gradient that is higher on one side than the other. And so these molecules can just naturally diffuse down to try to achieve equilibrium. But if you've got a situation where you've got something really, really, really important to take up, is that important to us? Oh yeah, big time.
It's a very magical substance.
It is.
We don't know what it is yet.
This is the perfect example. This is the perfect example of what your good exams are going to look like. I'm going to show you the answers, and you're not going to know which answer is correct because you got to guess what the question is. There we go. I wouldn't do that to you. So, glucose. Is glucose important to us? I'm going to bore the hell out of you talking about glucose in a couple of weeks. This is extremely important because it's our primary energy source. It's what we are going to be generating most of our ATP and our energy from. So would you, if you were designing your body, would you want glucose to come in by facilitated diffusion? So that if you ate a lot of glucose, you'd get a lot in. But most of it would end up flushing in the septic system? Or would you want something that would be active transport? Something that would use the power of another gradient to make sure you got every single molecule of glucose? Which one do you choose? Second one, right? So this is called the glucose sodium transporter. And this is secondary active transport. We're going to go into this receptor, this transporter, in detail next week. So now, the other type of transporters we have, you've seen this one in many parts of the block. Depending on the channel, these are ion channels. And these can be regulated by signaling molecules or electrical changes to change the conductivity of this receptor. And then we have others that are in the membrane. These are lipophilic transporters. Lipophilic means that they are soluble in the plasma membrane, and they can take material from one side of the membrane, bind to it, and transport it to the other side. We have a couple of our cases, I think. One of our cases will be looking at a poison that takes advantage of this particular transporter activity. Okay, any questions about basics of transporters? So these are generally the types of transporters we're going to be seeing throughout the block. Now, I want to make a note about these types of graphs and cell pictures, these diagrams. You'll see a lot of these where you've got a drawing of a cell, you've got transporters located on, for example, the apical side of the cell, being the luminal side, the interstitium, the tissue side, this is the basolateral surface, and you'll see transporters located on each side. These transporters are positioned in order to control the ion flux across these cells from the interstitium to the lumen. This is what's changing the ion concentrations in the saliva, in the secondary saliva. Now, the thing to be careful of these is these pictures are generally what you'll find everywhere. Textbooks, internet. I happen to pull this one out of the internet. If you try to be a good physiologist and try to balance, okay, here's sodium going down, potassium going up. Well, how does that happen? Sodium's going down here, we're taking sodium coming out here, we're pulling it out, we got protons going out, protons coming in, pushing potassium out. Okay, that might kind of be sense, but bicarb's going down, chloride's coming down, that's going to follow sodium, so the bicarb's going up. This is what you typically are taught to do, especially in physiology courses. Don't do that for the salivary gland. Because I used to teach this to our poor medical students back in 2002 when I started here. And we used to go through all of the transporters and make sure that everything was possibly balanced. And I destroyed brains in the very first week of this block by doing this. Because what happens is you go and you look at other textbooks because something might be off a little bit. Well, what's off, if we move from a resting state, from a resting state, we activate our cephalic phase of digestion. We trigger these parasympathetic nerve responses. We contract our myoepithelium. Our x-axis here now is going to be representing flow. Now notice the flow is measured in milliliters per minute. So as we increase the amount of flow, we can measure the concentration of ions in our secondary saliva. Now, under low flow rates, which is right here, this would be considered resting. We have numbers here corresponding to sodium, bicarb, chloride, and potassium that are very much what we've seen in our previous table. So under low rest conditions, we have the saliva being processed. But now as we increase the concentration of our flow, the concentration of sodium increases such that look where we're ending up. This is plasma concentrations. Concentration of chloride is increasing closer to plasma concentrations. Concentration of potassium is at that low value in the plasma. All this says, looks complicated, all it's saying is that as the saliva, you're going to love this, this is what the textbooks are, don't shoot the messenger, they say this. As the saliva is moving faster because of under that myoepithelial contraction, the striated duct cells have less time and opportunity to extract the ions because their transporters can't keep up. And it returns the concentration of ions closer to what you would see in the original concentration in the plasma. So it's a very, very simple, easy interpretation, but they give you all of this data. I think it's the physiologist kind of feeling, look what we did. Now, the one difference, and this is really critical, this difference, is the bicarbonate ion. So the bicarbonate ion is actually increasing its concentration as this salivary fluid is going down the duct. So that means that the amount of bicarb coming out of the cells into the lumen is dramatically increasing under stimulated flow. This is where trying to balance your ions by looking at these transporters will make you wonky, because there are other independent bicarb transporters that are not, they're decoupled, uncoupled from the chloride antiporter. And that's why I say don't worry about balancing this. But what's important is that the salivary stimulation, that parasympathetic stimulation, is also going to be in stimulating the striated cells. And by some mechanism that I could never identify in the literature, it's going to be increasing the activity, expression and activity of an enzyme called carbonic anhydrase. Remember that enzyme? I'm sure the CV block went over that one in detail. Converting CO2 and water into bicarb plus a proton. We'll be revisiting this one. And the bicarb is preferentially going to be secreted. The proton is going to be used by other transporters. So what is that going to do to the pH? It's going to go up. It actually rises by this much. 2 pH units. Remember, pH is a log scale. 2 orders of magnitude increasing. Now, why is a higher pH, a more alkaline solution important? What can an alkaline solution do to protect your oral cavity? Neutralizing acids. The majority of foods that we eat tend to be acidic. The first time I learned that was in a developmental biology course, because the professor took a Coca-Cola and poured it onto the overhead projector. Yes, that's how old I am. Poured it on the overhead projector, and he cleaned off the markings. And he said that's the only good use for this drink, because he said it's pH 5.5. So what does acid do to your enamel? degrades it, breaks down the enamel. So by increasing the pH, we're going to help neutralize that acid. Yes?
You wrote secondary saliva on the right there. Aren't those concentrations near primary saliva?
Yes.
Okay.
So in the secondary saliva, under stimulated flow, only under stimulated flow, that saliva is going to, we're going to sample it at the secondary site in the ducts, and the concentration of the ions will be approaching the plasma levels, simply because the striated cells do not have the opportunity to pull out those ions because they're moving so quickly. So by having some of this higher pH basic solution in there, what's another protective mechanism this can do? Burp. Acid reflux. So by having some of this higher pH basic solution, when we swallow, this solution is going to slam into, well, it shouldn't slam into that lower esophageal sphincter. It should be open and nice, ready to receive. But it's going to hit there and it's going to bathe that area in a pH of 8. Right across that sphincter, pH 2. So this is going to help protect from esophagitis. Okay, so now those are the ions. Now what else is in saliva? Oh God, here we go. Structures, biochemistry. You know I love this stuff, so that means you get to suffer. Major salivary protein, amylase. Remember the function of amylase. Amylase is the first level of chemical digestion. So what Dr. Shuttleworth talked about today and what Dr. Chang alluded to today was the process of digestion that starts in the oral cavity. It starts with a mechanical process, chewing, our jaws moving up and down to make those food particles smaller so that we increase the area of our food for digestive enzymes. Amylase is the first level of chemical digestion. So the amylase is the enzyme that is going to hydrolyze our favorite food source, starch. I always ask this of every class because I like to see what part of Europe people often came from. Name a starchy food.
Potato.
Wow. We've got potatoes. We've got bread. Rice. Yay, we got that part of the world covered. Okay, what about the part that looks like a boot?
Pasta.
Pasta, yes. I'm Italian. So those of you that might have said pasta will pass the block and you can go home now. So starch, you know, from listing those kind of foods, you know that those are major food sources that we eat, and so we have an enormous amount of starch. Starch is simply a polymer of glucose. And it's linked by an alpha-1,4 glycosidic linkage. Oh God, I know. It's that chemistry thing. But this actually turns out to be a board question. Yeah, you got to know an alpha-1,4 because of this here, beta-1,4. This also is a polymer of glucose. This is cellulose. Can cellulose be used as an energy source? No, absolutely not. Why? We cannot break this linkage. Why can't we break that linkage? Take it one step further. Don't have the enzyme. What is the enzyme? Cellulase, right, exactly. So that means you've already known by that extrapolation that amylase cannot touch a beta-1,4 linkage. Now, that means cellulose is absolutely useless to us. There's nothing good about cellulose. We cannot use it for energy. Is that correct? Before you answer, think about the block you're sitting in. Good. Nope. Because when we get down here in the GI system, we're going to talk a lot about cellulose. Cellulose is probably one of those things that you'll be dealing with. If you go into family practice or internal medicine, you're going to have a lot of older patients with bowel issues called constipation. And so you're going to learn a lot about cellulose and how important that is. So cellulose is very important to us, but we can't use it as a fuel source. So amylase. Amylase is made by our salivary glands. It's the beginnings of chemical digestion to start breaking that glucose down for absorption. Now, that being said, is amylase important to adults in digestion? What's another organ that we're going to be looking at? If you lift up the stomach. Pancreas, yeah. So the pancreas is the major digestive organ. That's the one that's going to secrete the biggest amount, largest amount, and volume quantity of digestive enzymes. We'll look at that later this week. So amylase, a little bit is in the saliva, and quantitatively, it is absolutely doing us no good whatsoever. So why the hell do you have to know this? I don't know. I don't write the step 1 questions. So a little bit is in the oral cavity from salivary gland. What is this is a basic scientist description, what is a form of human that amylase is important to?
Babies.
Babies, yes. Okay, all the moms in the audience here. Form of human. That's why we expose you to basic scientists only in phase 1, and then you never see us again. So why is it important for babies? Why do babies take quite advantage of amylase? What about their pancreas that's very unusual with newborns? It's underdeveloped. It takes 6 months to a year to fully develop the pancreas in order to be able to have all of those digestive juices. Okay, another major protein in salivary secretions is mucin. And the purpose of mucin is primarily to lubricate the food. So it's going to lubricate the food, lubricate the esophagus to make sure that food passes down very quickly. What is the structure of a mucin? Well, when I first learned about mucin, I always thought, you think about lubrication, and you think about oil. And I always thought that a mucin is a fat. It is not. It's as far from a fat as you can get. What a mucin is a structure of a protein. So if we have a protein that has an N and C terminus to it, and there's many different types of mucins, and they're largely named after the protein backbone. And they have lots and lots of additions to them. And these additions are carbohydrates. These are polymers of carbohydrates. Now, these are not polymers of glucose like starch. These are modifications of glucose. You can have galactose in there. Another type's called iduronic acid. We'll get into those later. But lots and lots of sugar that are covalently linked to this protein. This is the structure of all mucins. What this tends to be is very, very sticky. Take honey, lots of carbohydrates, put it on your fingers, it's sticky. That's what a mucin is for. It's to create this protective barrier that's sticky and also lubricates, because remember, sugars have hydroxyl groups all over them. And what does hydroxyl groups do in water? Hydrogen bond, yeah. So these mucins, they're sticky, they form kind of a gelatinous mass, and they also bind an enormous amount of water. And it's these two properties that allow these mucins to be able to coat the food and allow it to pass through the esophagus very easily. Questions so far? Our first level of immune surveillance, IgAs. So the IgAs are made by our immune cells, our B cells located in the submucosa. This is part of their surveillance immune system. They secrete the IgAs. The IgAs in secretory cells is actually a dimeric form. Remember, we have our two structures of our two IgA molecules, immunoglobulin A. And then this is our J chain, similar to our IgM molecules. But the IgAs are linked tail to tail by this J chain, and they are going to bind to the polymeric immunoglobulin receptor, the polymeric Ig receptor. Once they bind, they undergo a process across the acinar epithelial cell called transcytosis. And transcytosis is simply a vesicle that internalizes off of one surface and moves to the other surface and fuses. Once this is exposed on the luminal surface, now we have proteolytic activity that cleaves the receptor and releases the IgA polymeric Ig receptor complex into the luminal compartment. Remember all that from immunology? No? Oh, I gotta talk to Bryce. He didn't go over polyase? Okay, so this is generally, so there's two forms of IgAs. Anytime you have IgAs inside the body, they are going to be monomeric. Monomeric means just one chain, similar to the IgG structure. Once you have any kind of IgA that's going to be secreted into the lumen of the body, secretion, it's going to be what's called the polymeric form. And that's connected with the J chain. What you're forming here is a very complex, multivalent antibody structure that can recognize foreign antigens very efficiently. Okay?